Now, if you remember, a rational is just a fraction. That's just a big fancy math word for a fraction. So a rational function, what that means is we have a function of this form, where f(x), the function, has some function possibly with x's in the top, and some function possibly with x's in the bottom. Now, the one thing about this, in this form, is that the function in the denominator, the h of x, cannot be 0. And that's something we're going to look at a little more detail here, is h of x cannot be 0. If h of x was 0, then we would have a fraction where we have 0 in the denominator. And if we have 0 in the denominator, we can't have 0 in the denominator. So that's not possible. So here are some possible examples of rational functions. We have 5 in the top, x squared in the bottom. We just have a fraction. Now what we're going to do is we're going to look at this in a little more detail here. Is if this is our rational function, that means that if we put an x value equal to 0, if we made x equal to 0, we would get 0 in the denominator. And that would be our h of x. But we don't want that, so we say that x cannot be equal to 0. Those were what we called the restrictions. So in the first one, x cannot be equal to 0. Here's another function. G of x is equal to 1 over 3x minus 8. So in this case, we would say 3x minus 8 equals 0. So 3x is going to equal 8. So x cannot equal 8 over 3. So that would be the restriction, and that would be what the function, or the x value could not equal. And here's another fancier one, a little more elaborate, h of x. 4x minus 9, x cubed plus x minus 6. So these are just some typical examples of rational functions. Now we're going to look at something new, something called an asymptote. And an asymptote, again, the higher up in math we go, we get fancier words to make us look smart. And this is just another word to make us look smart, or a formal definition. So an asymptote is a line that a graph gets very close to touching, but never actually does. So we can have vertical asymptotes and horizontal asymptotes. A vertical asymptote is just that, a line straight up and down. So there's a line right here that the graph never actually touches. And if we look at this graph, it gets closer and closer and closer and never actually touches. And a horizontal asymptote, same thing. It's a line that goes horizontally. And there's a value that it never actually touches. Now, what does this mean mathematically? Well, to determine asymptotes mathematically, these are the values that, and I put it in quotes here, are not allowed in the function. So values that are not allowed in the function, the reason they're not allowed, and we talked about that before, is what x cannot equal. We talked about that in domain and range. All that means is we don't allow those values because there is an asymptote. So this is something you've already been doing, just haven't been formally told at this point of what that is. So we're just going to have functions, or we're going to have graphs that represent lines that cannot be crossed, and they're just asymptotes. And these are the values not allowed. And it says very similar to domain and range, and that's what we're going to look at in the next one here. So vertical asymptotes. And again, vertical is up and down. What we want to do is we want to determine the vertical asymptotes by looking at the denominator of the function. So it's all about the denominator when you're dealing with vertical asymptotes. And a vertical asymptote is any value in the denominator that makes the denominator 0. The vertical asymptotes are just the restrictions. So what do we have to do is we have to determine what the restrictions of this function are. We can't determine the restrictions until we factor this. Top's going to stay the same, 4x minus 9. The bottom's just going to factor. And I imagine everyone loves factoring. We're going to have an x and an x. And we're going to find two numbers that multiply to -6 and add to +1. So it just becomes x plus 3 and x minus 2. So that would tell you that x cannot equal -3 and x cannot equal 2. So those are the restrictions. Now, the equation of the asymptotes or where the asymptotes are just the solutions. So we're going to have an asymptote at x equals 3 and x equals negative 2. And we're going to say that the vertical asymptotes occur at x equals 3 and x equals negative 2. Now, what about horizontal asymptotes? Well, horizontal asymptotes are a little bit trickier. Not a lot, but a little bit trickier. The horizontal asymptotes are determined by examining the degree of the numerator in relation to the degree of the denominator. So now it's really looking at the entire rational function to determine where the horizontal asymptotes are. So we're going to look at the numerator, and the degree of the function in the numerator, this is just degree 2. And remember, it's just the power or the exponent. The highest exponent is the degree. The degree in the bottom, or in the denominator, is degree 1. Now, if the degree in the numerator is greater than the degree in the denominator, and these are things you just have to memorize. If the degree in the numerator is greater than the degree in the denominator, there are no horizontal asymptotes. So for this example right here, the degree is 2 in the numerator, degree is 1 in the denominator, so there's going to be no horizontal asymptotes. And that's fine. We can have a function where there's no horizontal asymptotes. There's no reason that there has to be a horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is at 0. So that's another quick one, is if the top is less than the bottom, numerator is less than the denominator, then there's a horizontal asymptote at x equals 0. It's this third one where we're going to be a little bit tricky here, is if the degree in the denominator equals the degree in the numerator, then we have to determine the asymptote by dividing by the highest power of x, and then we make this assumption that 1 over x is equal to 0. Now, what I'm going to do is I'm just going to show you why 1 over x is equal to 0. Now, if you go on and do math at a higher level, university and beyond, you're going to look at this in extensive detail. But let's look at 1 over x. And what I'm going to do is I'm going to make x really, really big. So you may or may not have seen this symbol before, but this is infinity. So we're going to make x go to infinity, as we call this. So what we're going to do is we're just going to take some possible values. So let's just make x really, really big. If we have 1 over 10, of course as a decimal that becomes 0.1. Well, let's make x even bigger. Let's make it 1 over 100. Well, of course, that's going to become 0.01. Well, let's make it even bigger. 1 over 10,000. That's going to be 0.0000. Oh, 0001. Let's make it 1 over a million. That's going to make it 0.000001. And as we can see, we have a trend here. We have a pattern. What's happening as we get closer and closer to infinity, as we make that x really, really big, our solution gets really, really small. So 1 over x, as we make x really, really big, gets closer and closer to 0. So as we can see, 0.1, 0.01, 0.00000001, those all get closer and closer to 0. So we're going to use that. And like I said, you're going to look at this in extensive detail if you do higher level math. So we just have to use this principle, though, that 1 over x is equal to 0 if we make x really, really big. So we go back and look at this. That's what we're going to do when the degree of the numerator and the denominator are equal to each other. So let's look at that in terms of an example to determine the horizontal asymptotes. So here we go. We have a function. And right away we know that the degree of the top is 2 and the degree of the bottom is also 2. So if the degrees are the same, what we need to do is divide by the highest power. Now, this has nothing to do with religion when we talk about highest power. We're talking about the highest degree. We're going to divide everything by the highest power. So we're going to take this function, and I'm going to take, oh, let's go back to black here. We're going to take 4x squared, and we're going to divide by the highest power, and of course the highest power is x squared. We're going to go minus 9 over x squared. That's just the numerator. The bottom is going to become 2x squared over x squared plus 3x over x squared plus 5 over x squared. Now when we simplify this, 4x squared over x squared just becomes 4. Negative 9 over x squared stays the same. Can't simplify that at all. Bottom, we're going to have 2 plus 3 over x, when we simplify that, plus 5 over x squared. Now this is where we have to use what we talked about before. 1 over x is equal to 0. Now it could be 1 over x squared, 1 over x cubed, doesn't really matter. All of that's going to equal 0. So we make x really, really big, and what happens here is all of these terms that have x's in the denominator are all going to disappear. And we're just going to be left with 4 over 2. Now remember, we're not trying to solve anything here. This doesn't give you any solution except what the horizontal asymptote is. So 4 divided by 2 is all we're left with, so we just get 2. So we have a horizontal asymptote, and remember horizontal is y, is going to equal 2. So in this question, if you're asked to find the horizontal asymptote, because the degrees are the same, we would have a horizontal asymptote at y equals 2.